In this lecture, I want to talk about the derivatives of inverse functions, and in particular the derivatives of inverse trig functions. So first, I want to talk about how we would find the derivative. If we knew f, how could we find the derivative of its inverse function? So let me quickly just begin with a quick review of what we mean by inverse functions. So some examples of inverse functions could be something like x over 3 could be f, and then the opposite of dividing by 3 is multiplying by 3. So that would be f inverse. And to kind of keep these separate, I'll use some different colors. So another one might be, for example, x squared. That could be f. And then, so if we just back up here, notice that they undo each other, right? So x, you take x, you divide it by 3. The opposite of that would be multiplying it by 3. In general, we have this property that f of f inverse of x equals f inverse of f of x, which is x. In other words, they just undo each other. If you start with a number, x, you just pick a number for x, and if you divide it by 3, and then afterwards you multiply it by 3, you get back your original number. Likewise, if you were to multiply it by 3 first and then divide by 3, you would still get back your original number. So another example is if x squared was f, what do you think the inverse would be? Well, what's the opposite of squaring? It would be the square root of x. That would be f inverse. Here we would have to make the further restriction know that x was a positive, well, non-negative, I should say, right? Because if x were negative, I could square it. I could take negative 3 and square it and get 9, and then take the square root and get back 3. But I started with negative 3 and ended up with 3. So in order for this to actually work, x would have to be non-negative. Another example that we'll talk about more in the next lecture is natural log of x. That could be a function. Its inverse would be e to the x. That would be the inverse function. Again, natural log of e to the x equals x, which is the same thing as if I did e to the natural log. But still, they both equal x. They undo each other, all right? So that's the idea here, is if we know what f is, can we find the derivative of f inverse? And the answer turns out to be yes. Well, I probably wouldn't be asking the question if the answer wasn't yes, right? Because it would be a pretty short lecture. So if we let g equal f inverse, then what we have a theorem that tells us, I'm not going to derive it, I know you're all breathing a sigh of relief now, that g prime of b, so b is just a number. It's an arbitrary number, but it's a fixed number. So if I wanted to find the derivative of the inverse function at some particular point, then I could find that by taking 1 over the derivative of f, which is the original function, evaluated at g of b. For this to be true, I need two things. This has two conditions. G prime of b has to exist. Alright, so in other words, if the derivative of the function doesn't exist, and this is nonsense, but also f prime of g of b can't be 0, because then we'd be dividing by 0, and that's not good. So this is our formula. What I want to do is apply this formula to the case. So we saw a couple examples up here of inverse functions. We have another class of inverse functions. So for example, I could have sine x, this would be f, then inverse sine of x, which is also, I'll just put it equals here, but it's really just a different way of saying it, arc sine of x. This would be f inverse. Likewise, we would have cosine and arc cosine, or inverse cosine, if you prefer, if you want to write that. Sorry, inverse cosine. So we could think about this with all the trig functions. Now, in this case, we would have to restrict the domain on sine x, right? Because otherwise, for example, you think of, sine of pi over 2 is 1. Well, that means that inverse sine of 1 equals pi over 2. They kind of just go, remember, one way to think about the inverse is that if the point AB is on the function, then the point BA, you can find basically inverse by just swapping all of the x's and y's, right? So, because what this is, another way of saying this is what value for, what angle, that if I took sine of that angle would give me 1, and the answer is pi over 2. See, we have that over here. The reason we would have to restrict the domain, though, is because if you think about the graph of sine, there's an infinite number of points where sine is equal to 1. So if I just wanted to look at this and say sine of what gives me 1, well, there's lots unless I restrict the domain. So what we look at when we do sine, we're not going to worry about so much about cosine, so I'll use this over here. So if I have my unit circle here, remember that any point on the unit circle, so if this is my angle, this point is given by cosine theta sine theta. In other words, the x value of that point is cosine of that angle, and the y value is sine, because you can kind of think of, I'm going to use another color here, right? So, because right here, the unit circle, so my hypotenuse is 1, right? So sine of theta is opposite over the hypotenuse, right? So, anyways, that would give me the y, right? The y coordinate here, this y, this height, we call that y, right? We would say that sine of theta is opposite over the hypotenuse, which is y. And if this is x down here, then cosine of theta is adjacent, so the adjacent side we can call x over the hypotenuse is 1. All right. So, in order for sine to have an inverse, we need to be able to do something like say that inverse sine of 1 gives me back one number, not an infinite number of numbers. It has to be just 1. Okay? So that means we need to restrict the domain of sine. So what we do is we restrict it to be along here. All right? So we go from negative pi over 2, right? If we started here and go backwards, we go to negative pi over 2 up to pi over 2. And notice that everywhere between 1, because this right here is 1 on the y-axis, this is negative 1, all these y values are covered if we just use this half of the circle, because sine is the y values. For cosine, we would restrict it from 0 to pi, because that would give us everything along the x-axis. Anyways, that's just an explanation of how we know the inverse sine of 1 is pi over 2, because we're using negative pi over 2 up to pi over 2. We could keep going around the circle and get, this would be, what if you added 2 pi? It would be, 7 pi over 2, and then do it again. You would get 11 pi over 2, but we're going to just restrict it to just those values. Okay, so that's just kind of a quick review of inverse functions, and especially the inverse sine function. What I want to do is use this formula right here to derive the derivative of inverse sine. All right, and this is just a little bit of a review that we need in order to kind of make sense out of how I'm going to derive that. Okay, so moving on, what we're going to think about now is if I take let's real quick put this formula back up here at the top. We have that g prime, and I'm going to do this for any x, not just a particular one, but the same formula we could use if it's a function of x. So that's going to be 1 over f prime of g of x. Okay, and so in this case, f, our original function, is sine, and g, which is our inverse function, is arcsine. or maybe I'll just use the inverse sine notation here. Okay, so if we use this formula, well, f prime is not hard, right? We know that that's cosine. Okay, so if let's just start off with that. We have 1 over cosine of inverse sine of x. Well, this isn't particularly helpful. And the reason is we'd like to get something in here. This is really an angle, right? If you think about it, we said that if we take, for example, sine of pi over 4, and that's square root of 2 over 2. So sine of an angle gives us back this ratio. So inverse sine of square root of 2 over 2, we're basically saying there's an angle, right, that if I took sine of it gives me square root of 2 over 2. So this would be pi over 4, right? This would be our theta, right, in the unit circle. You know, likewise, we could say inverse sine of, I don't know, 1/2. So the way to think about this is sine of what angle gives me 1/2. So this whole thing represents an angle, and it's going to be pi over 6. So what we'd like to do here is simplify this into something that we could get in terms of x. The inverse sine x doesn't really help us here, because the whole idea of this formula is that we can find the derivative of the inverse without actually knowing anything about the inverse function. All right. So here we kind of have to assume that we don't really know. I mean, this is for any value of x, this would not necessarily be a helpful formulation. We can do better. All right. So let's think about this then in terms of, we're saying that theta. Remember from what I did over here, inverse sine represents an angle. It's the angle that I would take sine of in order to get x. So if I take sine of both sides of this equation, I have sine of theta equals sine of inverse sine of x. Now remember before I said if you put the function with its inverse, you always get back x. So now I have that sine of theta equals x. So let's just take a look at a triangle for which that would be true. First, we know it has to be a right triangle because trig functions only apply to right triangles. Okay, so here would be my theta, and I know that sine is x. So one way to think about that is the opposite could be x, and the hypotenuse could be 1. Now this is different than the unit circle where this was y because I was actually in the plane. Now I'm just drawing some arbitrary triangle for which sine of theta equals x. I mean, we could call it y if you wanted to, but we have an x here, so that's what I'm going with. Okay, the question is, can I use, because this is a right triangle, can I figure out what this other side is? Well, I should be, right, because the Pythagorean theorem applies to right triangles. So what I know is that, let's just call this a. What I know from the Pythagorean theorem is that a squared plus x squared equals 1 squared. All right, so let's solve for a. Well, a squared equals, 1 squared is 1 minus x squared. So a equals the square root of 1 minus x squared. Now, technically it would be plus or minus, but because we're dealing with the side of a triangle, I'm only interested in the positive square root. So this is the square root, this side is the square root of 1 minus x squared. All right, so I'm going to come back to this idea then, cosine of inverse sine. Well, like I said, we can rewrite inverse sine as theta because it represents an angle, the angle for which if I take sine I get x, okay? So now that I have this triangle here, can I use the sides of the triangle to find cosine of theta? All right, well that's just going to be adjacent over the hypotenuse. So that's going to be, adjacent is the square root of 1 minus x squared over the hypotenuse, which is 1, so that's just the square root of 1 minus x squared. So if we put this all together, finally, right, so this cosine theta, that is my cosine of inverse sine, then what I get is that the derivative with respect to x of inverse sine equals 1 over the square root of 1 minus x squared. So just a quick review. Ultimately what we were looking for here, remember g was inverse sine. So just to make it clear, if I'm trying to find the derivative of inverse sine, I don't necessarily want the function in it. So that's why I needed to go a little bit further here, because just having inverse sine in here isn't necessarily going to help me. I want to find the derivative of inverse sine, so I wanted to get a different formulation down here, and this does much better for us. And we basically construct these triangles. I'm not going to go through all of them. Again, I'm sure you're happy about that, but I at least thought it was important for you to see at least one example of how we applied this general result of finding the derivative of an inverse function to finding the derivative of the inverse of the sine function. Okay, so now what I want to do is just kind of give you the rest of them without going through this painful derivation again. But again, the big idea, you would take this, you would come up with some formulation similar to this, and then you would draw a triangle, right? So if I was doing inverse cosine, I would have inverse cosine of x equals theta, which would mean that cosine of theta equals x. I could redraw a triangle for which that was true and solve for this side, and then I could get another formulation for sine of theta or cosine of theta as needed. Okay, moving on then. Let me just summarize our results and then give you just a couple quick examples. So we have the derivative with respect to x of inverse sine is 1 over the square root of 1 minus x squared. The derivative of inverse cosine is the same thing but negative. All right. So in fact, all of these will have kind of a partner. So there's two of them. You take the derivative. When I say a partner, I mean a partner that's exactly the same except negative. So if you take the derivative of inverse tangent or arctan, you would get 1 over 1 plus x squared. You take the derivative with respect to x of inverse cotangent, you would get negative 1 over 1 plus x squared. So finally, for the derivative of inverse secant, you would get 1 over the absolute value of x times the square root of x squared minus 1. Yeah, that one's kind of ugly. And then for inverse cosine, it's exactly the same except negative. Alright, so there's really only 3 to remember here. As long as you remember that co, and co are all negative, you can just really remember this one, and this one, right? Because the other 3 just the same except negative. So let's look at an example. Let's do the derivative with respect to x of arctan of x over 3. All right. So we have a composition of functions, so we're going to need the chain rule here. So the outside function is arctan, because it's arctan of, and the of is the inside function. So that would be x over 3, which we could just rewrite as 1/3 x. Easy to take the derivative that way. It's easy to at least to see the derivative is just going to be 1/3, right? So let's bang that one out right away. That's going to be 1/3. Okay, now f prime, well, that's easy too, because it's just right here. So that's just 1 over 1 plus x squared. So what is f prime of g of x? Okay, well, what I'm going to do is I'm going to take this x right here and I'm going to replace x with g of x, which is this. Alright, so I'm going to end up with 1 over 1 plus, and I'm going to replace x with x over 3. Square the whole thing, and then I multiply by g prime, which is 1/3. Right? If I'm going to simplify just a little bit, I can have 1 over 1 plus x squared over 9 times 1 over 3. So I can multiply this out on the denominator here. So the 1 times, well, multiply the numerators, I just get 1. And then I can distribute this 3 across, and I get 3 plus x squared over, well, this will cancel. I'll just end up with a 3 there. All right. I could keep going here, but this is a calculus lecture, not an algebra lecture. So if you want to keep going with that, you could probably make it look a little bit nicer. Okay, one more example. Let's take a look at something like the derivative with respect to x of inverse secant of 2x plus 1. All right, so again, we have a composition of functions. Chain rule is called for. The outside function is inverse secant of x, and the inside function is 2x plus 1. So again, g prime, very easy here, it's just 2. Okay, and then here f prime, well, it's ugly, but it's easy, right? So it's right there, 1 over absolute value of x times the square root of x squared minus 1. Now this is the part where it might get a little bit tougher because we're close, right? What we need is f prime of g of x times g prime of x. That's the chain rule. We have f prime, what we need is f prime of g of x, and then we're just going to multiply by 2. Okay, so f prime of g of x, f prime of g of x, what I'm going to do, in here, I'm going to take this 2x plus 1, and I'm going to put it in here for x, and in here for x. All right, so I'm going to end up with 1 over the absolute value of 2x plus 1, and then times the square root of 2x plus 1 squared. Again, I'm putting it in here for x, so I'm squaring it, and then minus 1 times 2. All right, I'm not going to go any farther with that. This could be simplified under here. You could think of this as 2 over 1, so you could make the numerator 2. But that just demonstrates how you might use some of these results right here. This is the main thing. These results are the main thing that you'll need from this lecture.